Okay, well, it's 12:12, so participants seem to have stabilized. Let's get the ball rolling. Hello, welcome to another exciting episode of our working group. Um, I'm Michael Meyer. I see some new faces or some new names on this Zoom call. So if this is your first our working group, welcome. We're a grassroots group of faculty, staff, graduate students here at Washington State University, largely at the Pullman campus, but also throughout the state. And each week we bring together a speaker, largely from our community, to talk about some R-related thing that the community has selected for that week. Or for the semester. So this week we have this semester we have a lot of varied talks. I'll throw a link in the chat to the schedule for the semester. But for this week, we're going to have, I'm really excited. It's our first person from the private sector in the 10 semesters that we've been running our working group, Bryan Shalloway, and he's going to be talking about feature engineering using lagged inputs. So with that, Bryan, it's all yours.
Thank you for the introduction, Michael. Oh, I think I might have the wrong page. Yeah, I was really excited to, I grew up, I live in North Carolina now and work as a data scientist for NetApp, largely in customer support and sales operations problems. But I grew up in the Squaxin-Mamish area, just east of Seattle, so I was very excited to get the chance to, speak out there. So I'm going to start my talk just with this quote. Time changes everything except something within us that is always surprised by change. And for me, working in organizational contexts, there's a lot of problems where time ends up making a difference. So there's obviously those where you're explicitly doing forecasting or working on problems that obviously require time series-based approaches, but there's also a lot of problems where you may take more traditional regression style approaches or treat the data almost like it's cross-sectional data, but you still may have relationships that vary across time, and you'll want to take those into account or take advantage of those relationships, even if you're taking kind of these more traditional style approaches. So that's kind of what the theme of my talk is going to be centered around, is how to do that and how to take advantage of that information. The three main areas we'll be focusing on will first be going through splitting data and giving a little bit of a primer on setting up time series cross-validation. Then I'll be talking about how to build features across time. And then I'll be basically putting this together into a model and a workflow and reviewing performance across these. Note that this talk, this is basically an adapted version of a blog post I wrote of the same name that you can find at my website. And this goes through descriptions in a little bit more detail than I'll probably go through here. Also, all the slides for this presentation will be posted at this location. And also just to note, in addition to what we'll be going through, so throughout both the code at the blog post and on the slides we're going through here, we'll be covering a wide range of packages in the tidyverse and also in the tidy models, which is essentially just an ecosystem with R that is made to play nicely with each other and have like an intuitive feel when writing code, and which I'm personally a big fan of. So I'm not going to be diving into how all of these pieces work. I'll just be kind of giving little tastes from each of these packages. At the end of the presentation, I'll pull up the documentation pages for each of these slides and other resources that were really valuable for me in terms of putting together the approaches that I'll talk about. Okay, so with that, as I said, I'm going to start with talking about data splits. And the data splitting is one of the early and really important steps in any predictive modeling exercise. And when I say data splits, I mean essentially we're splitting data into a training data set and some holdout data set. So you're building your model and doing any investigation on your training data, and then you're going to review performance of that model on your holdout or testing data set. And there's a variety of ways you can set this up. So that's kind of where this starts. So the most common way of doing this initial split is just randomly. So you'll have some set of observations that fall into your training data set and some that get put into your testing data set. And this is the most common approach. You may have some kind of stratification across, say if you have, you want your target to be represented similarly across your training and testing sets, you may stratify across that. But other than that, you may just have like a random split in the training and testing sets. Another common approach for setting up training and testing splits is across groups. So picture, for example, you may have regions or environments or customer transactions where those observations are not actually independent of each other, because they have some relationship with them. And in these contexts, a lot of times it may make sense to make sure that all observations from an individual group land in either the training data set or the testing data set. So in this case, all the triangle groups, all of them get pushed into the testing set, and then none of them exist in the training set in this context. And the reason this may be important is, again, you want to make sure there's not any leakage between your training data set and your holdout testing data set. And if you allow observations that are independent of each other in this way to exist across these groups, you're kind of, you're leaking information in your holdout set, and it's no longer truly this like separate entity. So that's usually why you're wanting to be thoughtful about how you're setting up these splits. So another kind of split that I'll be talking, this is the kind of split I'll be talking about today, is around time. So this is kind of a similar notion, but in this case, what we're doing is basically observations up to some point are going to fall into your training set, and then all observations after that are going to be put into your testing set. And the most common example of this is when you're doing forecasting, but setting up the split can still be valuable in other contexts. So again, I said, even if you're not doing forecasting, this can be helpful if you think that there's a chance that the relationship's not independent across time. One other nice thing about this split is that it often mirrors how models get put into production, in the sense that you may have data up to some point of time that you build your model on, and then once you built that model, you put it into production, and then it's going to be now producing predictions on whatever thing is of interest out in the wild, per se. So whether that your retraining period it could be you retrain this model every hour or every day or every month or every quarter. That like idea that you have data up to some point and then now you're gonna have to start making predictions. That process really mirrors a time-based split. So and especially in organizational settings like the ones that I work in, this kind of data split can make sense in lots of settings. Some of the things to be thoughtful about is just that any effort you put into any step of predictive modeling takes more thought and effort. So there's always just that balance of you can't do everything exactly the ideal way in all circumstances. It's this balance between getting value quickly and doing things that you have the time to do. So it takes more thought to set up an appropriate time-based split. Also, sometimes it may not make a difference. There's situations where maybe there's some slight differences you see in the performance metrics, but the actual type of model you select may not be hugely different. And then also, I'll talk briefly about cross-validation. You may sacrifice some data when using cross-validation data splits, which I'll just talk about in just a second. So just to say that it's not universally that you should always use time-based splits, but in the context I work in organizational settings, a lot of the times I think it makes sense. And I think it's going to be a really, really helpful thing to know kind of how to handle and how to split your data appropriately. Okay, so now I'm going to talk about cross-validation. Cross-validation is an approach I use very, very commonly in terms of when I'm trying to get a sense of the performance estimates for any models I'm building. So typically cross-validation is set up where you take your training data set and then you set up splits 5 different times, okay? Or not 5 different times. This is 5-fold cross-validation, but some amount of different times, depending on how many times. There can be different numbers depending on what kind of cross-validation you're doing. But this is an example of 5-fold cross-validation. And all this means is that each of these splits you're going to have a different set of observations that fall into your testing set. So in this example, we have these blue observations represent times when the observation was sent into the training set, and then red represent it being put in the testing set. So we have our initial training set. We split it 5 different times. 4 of those times, an observation is going to be in a training set. 1 time it's going to be put into assessment set. So you have these. It gives you basically multiple times that you're evaluating the performance within your single training set. The process usually is then, so you have these 5 different splits you've made, and then you build the model on the training set within each, and then you evaluate the performance on the new testing set within each. And then you can either look at the performance across those individually or look at the aggregate performance across all of your splits. One just note in terms of wording here, when you're doing resampling exercises like this, a lot of times, instead of saying the training data, you'll sometimes say analysis data set. Instead of saying testing, you'll say assessment data set. So this is terminology I'll be using here. This is also terminology used in the R sample package. Essentially, it's just saying the analysis set means that's the data set within this split that's being used to build your model on. And the assessment set is basically within this particular split, the data that was held out and is going to be used for reviewing the performance of that model within that individual split. So just to know that I'll be using analysis and assessment set as kind of like pseudo synonyms for training and testing set, but usually it's referring to these individual splits within your data. So this is an example of just random, like if we're doing a random sample with cross validation, that's what this setup looks like. For time series cross validation, it's a little bit different setup. Again, we have different assessment sets in each case here, but what's different is that you're going to have your observations up to some point, and then your assessment set follows after that. There's actually a variety of different ways you can set up time series cross validation, but all of them generally have that feature where observations up to some point fall into your analysis set, and then observations after that will go into your assessment set. So in this case, we're doing one step ahead time series cross validation, where you just have one observation in your assessment set for each individual split. This is a common process setup, and again, there's different ways of making this. I mentioned that there were some downsides with time series cross validation. Note that like for this particular split, you're not using all of your data. So that's a downside in the sense that you're not using all of your observations to train your model here. So if there's not actually any potential difference in the relationship across time, then you don't just want to use time series cross validation every time if there's no point, because you do lose some data in this case, and there's other potential downsides. But as I said, there's lots of settings where it does make sense to use, and I use this method frequently. In terms of why you would use cross-validation, also I just described what cross-validation is. Like, why would you bother setting this up instead of just using a simple training and testing set and being done with it? One value is that it allows you to evaluate your model without having to touch your testing set. So you could, you take your training and testing initial split, then you just take your training set, and now you can play with this and review the performance of models just on that set without ever worrying about like overfitting onto your testing data set or touching your testing data set. You can like hold that out till the end. So that's one advantage. It allows you a good way of evaluating performance and exploring things without ever having to touch that data set that you held out. Sometimes it's also used in place of having a testing data set at all. And because one other, I think, advantage with this is that because you're doing this multiple times across different samples, it can in some cases provide a better estimate for performance, or it can give you a sense of the variability of expected performance of your model too, because you can see, okay, I performed this well in one set, this well in another, and you can get this notion of, okay, what's the kind of like typical range of performance estimates I should expect to see on a model in this data set. Downsides with using cross-validation are, again, it's just extra step, extra time. If you're building a model that's really time intensive or compute intensive, rather than just building one model for your training set and reviewing on the testing set, you have to build separate models now for each of these individual splits. So it's a lot more models you're building. Some model types are designed such that this doesn't actually lead to huge computational increases, but there's some model types that it does lead to a lot heavier computational loads. So there are downsides to using cross-validation, definitely. But it's something, again, I use most of the time when feasible. Okay, so that was the primer on data splits. Now we're going to start going into examples. And the data that we'll be using here is from Wake County food inspections. This is Wake County's Raleigh, so this is near where I live. I live in the Raleigh-Durham area. And this data is essentially the fields we have are HSIS-ID, which is the restaurant ID. Then this is the inspection score. So this is essentially like, is the restaurant clean, safe for people to go and eat at? So you have inspectors in the state that go in, or in the county that go and review restaurants to make sure that they're following all the appropriate health protocols. And then we also have who's the inspector doing that, what date was the inspection. And for this kind of toy problem that we're going through, the target is going to be predicting score. So what's going to be the next food inspection score? Again, this is more just like a made up toy problem, but maybe a potential use case would be that you want to prioritize which restaurants you need to go and inspect. So if you think that they're going to have a really good score, you may say, oh, I don't need to inspect them quite as frequently as ones that I'm concerned about. That's like maybe a toy use case for this. problem, is that's why you may want to predict what the score is going to be. Okay, so now I'm going to talk about setting up splits using the R sample package here. And in this problem, we're going to say, we're going to be using date that the inspection is occurring as kind of like the date that's what we're going to be using to set up our time-based split. So let's just first set up our initial split. So we have this date time feats data frame here. This is like a data frame, and we're just going to order all of our rows based off of date. So we're just using the arrange function from the tidyverse to do that. Then we're using this initial time split function from the R sample package to say, okay, take the first 80% of rows and put that in. Those are going to be long in your analysis set, or really in your training set. Then take the last 20%, and those are going to be in your testing set. If I were to actually print this initial split object that I'm creating here, it would print out and say, here's how many observations are in your analysis/training set. Here's how many observations are going to be in your assessment/testing set. And then here's the total number of observations. So if I were to print this, that's what it would say. To actually then get the data frames from this, I then use these training and testing functions. So this is just going to create my train data set, which has, those first 80% of observations. And then this is going to create the testing data sets. This is my next 20% of observations. So this is just, I'm just making that initial split. Okay, so that was setting up our initial train and test split. Now I'm going to take my train data set and set up my time series cross validation on that. There's several functions within the R sample package that make doing this, I think, pretty intuitive. I'm going to be talking about the example R sample sliding period. So let's just walk through that. So here we have our train data set, which we create. This is our training data. We're going to specify the index. We're just putting the column name that is whatever index we're using to split this by. So in this case, this is date, just represents the date of the inspection. Then we're specifying the period. So this could either be like day, month, quarter, year. This is just going to be in quotes. It's saying basically like, how do we want to, what are the period lengths that we're going to be talking about? And then we're going to specify look back is going to say, okay, how big do I want my analysis set to be? So I'm saying when I say look back equals 36, I'm saying I want my analysis set to be 36 months. And then I want my assessment set to be, 3 months, essentially, is the setup. And then between each split, I'm going to be stepping forward 3 months from there. So when and I'm going to walk through what this looks like in just a second, but that's kind of like walking through these arguments. I'm specifying those parts and then building out this time series cross validation, how I want that to look. If I were to print resamples, what I would get is I have each row is going to have the ID associated with it, so that this is just each slice. So this is like a different sample. And then this is a list column where each row, each cell here represents an individual R split object. So that R split object I showed before that had the number of observations, the analysis, assessment, and total set, and you could use training and testing functions to extract that. That object exists in each of these cells. And again, you could pull out the training and testing sets from each of these. But so just looking at this though, you may want to validate your thinking and see, okay, did I set this up correctly? So I just have a few helper functions that I made that I'm loading in from this gist. This first one extracts the minimum, like basically the start and endpoints for the analysis and assessment sets for each split. And then this function just plots those using ggplot. So this is a good way of like validating, it's like a good sanity check to see, okay, did I set this up correctly? And in this case, it looks like it did. I'm saying, okay, my analysis set, that's, 3 years for my analysis set, and then a 3-month assessment set. And then for my next split, I'm jumping forward 3 months, and then each of these, and then so you can see, okay, it looks like I set this up the way I was expecting that I was. So this is just a quick sanity check that I'm doing here to make sure, okay, my resampling structure is set up correctly. So that takes us through then, okay, how I would set up that resampling object for our problem. Now I'm going to talk about feature engineering in this context where we're thinking about time. And I think one thing that's really important is to remember that, when you're setting up this training set and this testing set, this holdout set, the whole purpose of doing that largely is to be careful about data leakage, to make sure that, the parameters you're estimating on your training set are there's not any information leaking into into that process. So at the same time as you're careful about estimating your model parameters without worrying about data, with being free of data leakage, you also need to be careful about thinking about estimating your parameters for your feature engineering steps. So not just the parameters for your models, but the parameters for your feature engineering steps. So I'm going to talk about that in just a second. And let me break this. It's easy to break this down into 2 steps. There's kind of 2 steps with time-based feature engineering. The first step happens where you're actually doing like the pre-processing step, and the second step typically happens after you've made your initial time-based features. But it's easier just to walk through an example. So let me do that. So let's go back to our problem. We're trying to predict inspection score, and just take 10 seconds on your own and think to yourself, what features might be valuable for predicting a future inspection score for some restaurant? Just take 10 seconds and think through that.
Hey, Brian, we also have a question in the chat.
Okay, sure.
Sorry about that.
That's okay. Yeah, this is good because we're about to get into feature engineering. So if there's any questions on the sampling, this is a good time.
Could you sort of walk through an example of data leakage from this example case? And maybe, like, I know feature engineering might be a new term for some folks. Would you mind giving like a broad overview about, and I know a lot of these can be discipline specific terms, where it's like, I know what it is in this discipline. But
Thanks,
yeah.
Michael.
Mm-hmm. Yeah. So in terms of when people talk about feature engineering, it just basically means you're creating or modifying like your raw data and putting it into some form that's going to be useful for a model to have some kind of prediction based off of it. So I think it might be helpful just to see some features I'll create here. So if you were thinking through what information might be useful for predicting the upcoming score, features I thought of here would be, okay, what was the most recent score? You know, for a restaurant, whatever its most recent score might be relevant for predicting what its future score is going to be. So that's, you know, you may say, okay, I want to create a feature. Basically just means like making a new column where whatever the most recent score is for this observation exists in that column. Another feature might be how long ago was the restaurant last opened? So that means, you know, you make a new column that says, okay, for this particular inspection, how long ago was it last open? That may be a valuable piece of information for predicting what the next score is going to be. So whenever you talk about feature engineering, it can mean like a lot of different things, but generally just means you know, building some new variables or that the model can use to, you know, predict something. Sometimes the features are useful, sometimes they're useless, but usually it's just like the process of coming up with those. Or there's a lot of different ways you can go about it, but I think that's the most simple form or like way of thinking about it. The other question was about an example of data leakage here. So an example of data leakage in this case, which I'll walk through in just an example. Let's say that, okay, here, so let's look at a couple other features. And one of these I'll have a good example for.
Oh. I don't know, Henry and I looked at the GSA rates and we were gonna base it off of.
Okay, so how long since last inspection? This is like another feature. I mentioned how average score across restaurants for the last year, average score for the particular restaurant last 3 years. So let me use these as some examples of potential data leakage. Let's say we're wanting to predict what the future inspection score is, okay? And we have our data set, and in our model, we build a feature that just says, what's the average, that takes the average score across restaurants in general, including inspections that occurred up to that point and inspections that occurred in the future. If you just take the average inspection score across current inspections and future inspections, now that feature has information that you wouldn't actually have available at the time of producing a prediction in real life. You're not going to know what future inspections are. So if you were to add that feature on, and then incorporate that in your model is going to say, oh, I'm doing, you know, it may do a really good job, but it may only be doing a good job because that feature that you built was using information that wouldn't actually be available at the time that you actually would have to make these predictions. So that's like an example of data leakage. It's just information that really wouldn't be available to the model at the time of producing a prediction. And then it's when you are evaluating your performance based off of having made that mistake and saying, oh, my model performance is this good, and that's not an accurate representation of how good that model actually would be if it had been trained in a way that's appropriate. So in terms of setting up these like proper data splits, if you if you're doing feature engineering or doing some of these things without having that split in place, you may end up building features that, have this leakage issue because they're taking in information that wouldn't be available at the time of prediction in real life. So it gives you an inaccurate notion of how accurate your model is going to be.
Cool.
Thank you. Okay, so yeah, so now we're talking about, so on to feature engineering then. So all of these features that I just described here, I said there's 2 steps to feature engineering. The first step happens usually during pre-processing or right after pre-processing. And all these features, the reason these happen right after pre-processing, generally, this is before you make your data split, before you set up your cross-validation windows, before you do any of that. You need to actually generally make some of these features before that, because like take this example of the average score for an HSID over the last 3 years. If you were to look, let's say at an observation, an inspection that occurs in 2017, and you said, okay, for this inspection, what was the average score for the last 3 years? After you've already done your split, you don't actually have that data here. So that, you don't have the last 3 years of data in this particular split. So instead, what you'd want to do is for this feature, you need to make it beforehand. And then after you've made all these features, then you can set up your splits. So any features that you're building that are like reliant on like lagged observations or observations that go across time, you generally will want to make those prior to setting up your data split, because they may be reliant on observations that happen beforehand. However, when doing that, you need to be thoughtful, because you also don't want to set up a feature that's going to have some data leakage issues, that has, that's taking information in the future that's not going to be available at that point. So I'm going to go through an example of building a couple of these features and like how, what functions I will commonly use to be careful about that. So when setting up the sampling windows, there were all those, sliding index, sliding period, sliding window. There's a complete analogy between those functions and these functions in the slider package that are used for essentially doing these operations across windows. So they work really similarly. The syntax is the same. It's by the same person that made those functions made these. That's one thing I keep mentioning about tidy roots. There's like this consistent style, which is really nice. So let's, I'm going to walk through this example where I'm going to create the average score across HSIDs for the last year. So we're just saying, maybe recent inspection scores is relevant for predicting future inspection scores. So what I'm going to do, I've got my raw data here. I'm going to arrange it based off the date of the inspections. And then I'm using this function slide index double. And what I'm doing is I'm going to specify, okay, what's the column? What's the data that I'm going to be passing through? So scores I basically want to be getting like a moving average of score over time. That's what I'm basically creating here. I want to see what's this moving average of score over time. I have to specify what the index is going to be. That's my date column, the date of the inspection. And then I'm specifying what function I want to do. So in this case, I'm doing mean. I'm applying, just give me the mean inspection score. But you could have this be any function you could have that you could imagine. On their website, they have some examples of like passing through modeling steps in this process. But any kind of function transformations you'd want, you could use as your function here. Then though, these dot before and dot after, these are specifying essentially the window. So these functions are often used for like making moving averages here. What I'm specifying here is I'm saying, okay, give me a moving average of score that's 365 days in the past up until the day before whatever my current inspect data is. So this dot before is saying I'm going back 365 days. The dot after, in most cases, when you're building a moving average, you may be looking like 3 days before, 3 days forward, and then you're getting a moving average of that kind. In this case, though, because we don't want any data leakage, I have to specify my dot after to be negative, because I'm saying I'm not actually going forward any days. I'm going backwards to the day right before whatever my current inspect date is, because I don't want any information leaked from that point on into my average prior inspection score. So that's what I'm doing here to be careful that there's no data leakage issues, because basically I'm saying any information up until the day before this inspection was taken, that's going to get factored into giving me this, my moving average of scores across the board. So this is an example then of creating this this recent overall score. I'm going to walk through a second example where I show how I would create the average score over the last 3 years for each individual restaurant. So in this case, again, I'm taking my raw data. I've already arranged it by date. Now I'm saying let's group by the restaurant ID. And I'm going to now use, again, that same function. I'm saying score, my index is date, mean. This time I said I want to do prior 3 years. So I'm doing, over the last 3 years, up until the day before this current inspection, give me the mean. And because I grouped this by the restaurant ID, this is going to give me the average, the 3-year average, like three-year prior average of score for each individual restaurant ID for that particular inspection. So this is going to work, across all observations in my data set. So that's just 2 examples. After having done those, so I just showed making the score year overall, score recent, but all of these kind of features you'll often want to do in this kind of like pre-processing step, but still being really conscious of, let me make sure I'm calculating these in a way that isn't going to have any data leakage issues. Okay, so that was step 1. After we've done that, so the first step is basically all that happens before your data split, as I said, because you may be needing to look to prior lags of your observations. So after you've done that first step, building all your time-based, lag-based features, then you can apply that initial split, create the resampling object that I showed around the time series cross validation. So basically, just picture applying all of that now after having done that feature engineering. Step 2 comes after that. The next step is basically any other features you want, or any like transformations on those those time-based features that you just created. So examples of these may be, so box Cox transformation. This is like, say you just want to transform the distribution of your data. Box Cox transformation is one way of doing that. But to do that, you have to estimate certain parameters. And you want to estimate those parameters on your analysis set, not on your assessment set. Because again, if you re-estimate those parameters on your assessment set, that's potential data leakage because you wouldn't have that information at the time of prediction. So these are some other kind of transformations you might do. But none of these steps, these are all being done on basically like your data you've imported up to this point. They don't require earlier lags of information to do these kinds of operations. Hence why I'm saying this is kind of like a separate step. Another feature you might want to make is you may want to incorporate the inspector, who the inspector is, to try and predict what your inspection score is going to be. And there may be some cases where you have like rare levels, people that haven't given that many inspections, and you want to collapse those all to other. Like if you have less than 50 inspections for this particular inspector, they should be counted as other. You may also want to take out parts of the date. So maybe what's the month, what's the day of the week, et cetera. Those types of information may be useful for predicting the inspector score. These are just a few like potential features you might make, but none of these are based off of lagged information. That's kind of like the distinction here between the step 1 and step 2. And for these steps, there's a really awesome package, recipes, in the Tidy Model Suite that makes this pretty easy. And what it does is it essentially, like this example of the box Cox transformation, it will identify what those parameters are for doing the feature engineering step on your analysis set, and then we'll apply those parameters onto your assessment set for you, so that there's, it does that for each of your individual splits. And also, again, this works really well with the Tidy Model Suite. So I'm going to walk through just an example now, again, of going through this kind of step 2, setting up a recipe for building additional features. So when setting up a recipe, first I'm going to specify, okay, my target in this case is score. I'm going to be predicting score based off of all of my other columns in this case. I'm going to have a step where I say step box Cox. So I'm going to say let's do box Cox transformations on days since open and days since last. I'm going to say for inspector and type, these ones I'm going to collapse to other if you have fewer than 50 observations. If there's any new any new levels that come up, those are also going to get collapsed to other. So these are just like, there's a whole, if you go to Recipes website, they have a ton of different steps you can use. And what's really nice about each of these is that it makes it easy to, estimate the parameters relevant to the transformation, and then estimate those on the analysis set, and then apply those to the assessment set. Okay, so at this point, I've specified the resampling object. I've specified a recipe. So I specified the resampling object. I've done my feature. I've specified my recipe for my feature engineering. Now I'm going to specify my model and then build out a workflow. So the package parsnip is used for basically giving a generalized interface for models. If you're familiar with Carrot, this is essentially like the Tidy models follow up to that. It's by the same author that made Carrot, is the lead developer on this. So what I'm doing here is I'm saying, okay, I want to make a linear regression model. And I'm going to say, let's set the engine to be from to be using LM. So this is like, if you're familiar with regression R, LM is like really common function for doing least squares. But if there's other packages you might want to use, like for example, there's glmnet for using regularized regression. There's Stan if you want to be fitting Bayesian models. You could change this engine to use other types of linear models. That's kind of like the advantage of Parsnip, is it gives this unified interface that has consistent argument names, and that you can then also works really smoothly within the Tidy Models framework. And then I'm setting the mode just to say this is a regression problem. If this was a classification problem, I would say set mode classification. So now that I've specified my model, specified my resampling object, I've specified my model, my recipes. So I'm going to say, okay, let's initiate a workflow. Let's add my model to that workflow. Let's add my recipe to that. Let's add my resampling object. And now it will apply the recipe to each analysis set, and then apply whatever parameters identified there to the assessment set, and then build the model, and then evaluate the performance on the assessment set. It does that for each of your within your resampling windows that you've set up. So let's just pretend I did the same thing across multiple models. Maybe you're building a linear regression model as well as a random forest model or a few other types, and you want to compare performance across those. So pretend I just did this exact same thing, but for random forest. And I'm also going to do a null model type just as like a baseline comparison. The null model is just going to be what the mean score was. So say I've done that, extract performance, and I'm going to compare models. I'm going to walk through this in a little bit more detail at the end, but for now, just pretend I've done those steps. And now I am reviewing the performance across each of these splits. So I have my root mean square error and my R squared. And then I'm seeing, okay, it looks like my linear model is slightly outperforming my random forest model, both of which are doing better than just the null model. So you could look at the red line and green line represent the average performance across the cross-validation splits. And then on the y-axis, we have each individual split, so you can look at it in each individual one as well. And if you're trying to think, okay, is this difference between linear model and random forest model really different, or is that just something you'd expect to see as a result of random variation? You could do a pair t-test and check it, and if you do, you'll see, yes, there's a true difference. It seems like this difference is unlikely to occur just due to random variation. Okay, so I'm going to pause there, and then I'll do a recap, and then I'll pull the actual code up for this if there's any questions that have come up. Because we just went through a lot.
How would you? Hi, how's it going? Yeah, this is really cool. How do you just mention using a t-test to evaluate that? Which one would you conclude is the superior one, the linear model fit or the random forest? I wasn't.
Oh yeah, in this case, the linear model is the one that's doing better. We see. Whoop, I went back too far. So when I do the I'll pull that up. But when you do the t-test, you see, yeah, there's a significant difference where the root mean square for the linear model is going to be less than it is for the random forest model, and you also see the R squared is higher. So more of the variance is explained by the linear model compared to the random forest model. So if you do t-test on pair t-test of either of these, you'll see the linear model comes out as being significant.
Is the t-test on the distances of like the colored dot from the specific line?
So you could just do a t-test, just taking the difference, and just compare it against 0. That's one way of doing it. You could also do a pair t-test where you incorporate just the observations from both. So either way, I think gives the same results. So yeah, you could take the differences and just do a regular one sample t-test as well.
So just to clarify, because this is really cool, I'm trying to learn how to use these to forecast insect outbreaks in agricultural systems. So the point is the prediction based on the training data set, and then the line is what your validation set is expecting?
I'm glad you asked that. So each of these points are actually the assessment set performance. So this is sliced. So for this particular slice, this is the performance on the assessment set for the linear model. This is the performance on the assessment set for the random forest model, and then this is for the null model. What this line that I have that's going over everything is if you take the average of all the red points across the board, yeah, so this is just showing the aggregate difference. Yeah, so this is each individual one for each individual split is the points, and then the line is the aggregate difference across all the splits. I should have made that explicit.
So I assume lower is better.
So for RMSE, lower is better. For R squared, higher is better.
Got it. Awesome. Thank you very much.
Yeah. Any other questions? Just on, yeah, what I just went through there on modeling.
I was curious about the step where you're setting your engine or setting your mode. I was looking at that actual linear regression function, and it looks like, you know, you can set it within the function's parameters, but you can also use the set engine or set mode as, you know, separate lines. What's the benefit of going about that approach?
Could you say that? So could you maybe just ask the question again? I think I'm a little unsure. So what's the advantage of doing this versus just doing like LM directly and not having using the setting up the parsnip object specification? Or maybe just ask your question again and I'll get it.
Oh,
better.
yeah. So within the parsnip package, the information for that linear or linear underscore reg function, you can set mode directly equal within like the parentheses there. But then you can also use that separate set engine or set.
Yeah,
mode.
what's the advantage of having this be a separate line?
Yeah, I know
Yeah.
it's probably just a syntax thing, but I was just curious because I haven't done that kind of stuff.
Yeah, I would say it's a little bit more of a style thing in the sense, yeah, you could say the mode here. So in terms of what each of these parts are for, so in the linear reg, most of the arguments that you put in here will be ones that are like generalizable across model types. So like if you're doing, say you're building a random forest model, you know, or any tree-based model, there may be like number of trees. And if you're using the ranger package or the random forest package or whatever engine you're using, they're gonna have really similar argument types. And usually you put all those argument types into this linear reg part. The set mode part will, you know, I would say it's maybe just a style thing. I was gonna say that each of these parts have like different places where you put those arguments. So in the, I'm actually forgetting now if you'll put like idiosyncratic arguments that go into the model, either into the set engine or set mode parts. I'm actually forgetting which one they go into, but it's kind of like I think it's more of a semantic thing where it's like, okay, you're doing this step by step, like do this, then do this, then do this. But there's some flexibility in terms of how you can actually input these arguments.
Okay, yeah, that makes sense. And then also I see that there are a number of different engines that you can use, like Stan, Spark, and Keras. Does that require additional like installation, or does that come with Parsnip?
So Parsnip, if it installed all of the model types underlying it, it'd be like a huge install. So Parsnip itself installs like some of the core stuff. And then if you want to use Keras, you just have to make sure you have the Keras package installed. Same thing if you want to use Ranger for random forest models, you just need to make sure you have the Ranger package installed, and then it will access that in terms of building it. So those things are installed separately, but they're just like other R packages you have to have installed. So install that package as Keras. Keras has other dependencies around Python and some other things, but it should just generally, it's just like installing other packages that you have to have. Yeah, does that answer your question?
Yeah, it does. Yeah.
Okay. Any other questions up to this point? Okay, so just to recap all the things that I covered. So one was to be careful with your data splits, especially concerning time, and to be thoughtful about potential risks of data leakage there. Build time-based features in pre-processing. Build any other features using recipes. Use cross-validation if appropriate, or if there's not like huge time constraint reasons not to. Try multiple models, and then review performance across splits, both in terms of what's the aggregate performance, but also it can be helpful to look at the performance within individual splits as well. And then I use the tidyverse and tidy model package, which I think give a smooth way of doing this. So these are just kind of like some things that I think are common things that I apply when working on problems like this. So here's links to the documentation for the various packages I went through. And then these are some other resources. This top one is the link to my blog post. This one's the GitHub page where I'll post these slides right after this. And then some other, this is Tidy Models with our Tidy Models website, feature engineering. These are all like other tidyverse friendly modeling or time-specific resources. So are there any other questions? I could pull up the code and just walk through that, but I kind of went through all the code too. So if there's any questions, I think it'd be more valuable probably to touch on those. Just really have a couple minutes.
Yeah, I read through your code while you were talking just to see if my computer would handle it. And actually my memories got almost maxed out by a couple of those functions. But I did notice for that last step, or I guess maybe it was the step previous, I kept getting some warnings about slice, preprocessor, NANDs produced. And I was curious if that's if that's normal or to be expected.
You know, with that, if you want, you can send me the error message on Twitter or something. Just send me a DM and I'd be happy to look at it. I'm guessing that may be the case that there's like some, so what could be happening is that there's some NAs that I'm creating. Like, let's say I say go back 3 years, but there's only a year and a half of data. Maybe it'll just fill it with NA. So I'd have to see the specific one there. Yeah, and double check that exactly. It could just be that there's some warnings around how the function's written that I need to be clearer on. So I'm not sure. It's tough to, I'd have to see it and which step, and then I can say what's going on.
Yeah, that makes sense.
Yeah, so it could be an issue where maybe I wasn't careful with how I wrote it in this example. It could also just be that maybe my syntax should be a little bit cleaner. It's telling me to write something different. I'm not sure. But yeah, feel free to, at Shallow, which I have at the bottom right here, feel free to DM me on Twitter or Bryan Shalloway. I'm on LinkedIn too. If you go through this and you're curious, I'm definitely happy to like answer any questions that come up for you. Or post a comment. Also, I allow comments on the blog post. So if you have like a question there, you can post it and I'll try and respond.
Thank you.
We still have a minute or so if folks have any last minute questions.
Oh, thank you. That was great. I think there was just some terminology differences because some of us are from like a quantitative ecology background, so we like have the training in statistics and data science, but like I don't think I've ever seen the term data leakage like in my field, but I know exactly what you're talking about when you described it.
Yeah, I think it's like just interesting. Even people that are in really similar spaces, there'll be this, it can just be like, yeah, you're talking about the same thing, but you are missing each other just based off slightly different terminology.